Okay, so good morning all of you, and can you hear me now, and can you see the video clearly? If yes, please say yes. We'll continue the class. Are you able to hear me and see the class? Okay, so now see here. So in yesterday we have solved previous gate problems based on entropy, and we have seen how application of basically the entropy balance equation, how we have applied there. So now before going for exercise straight away, there are a few little things that could take 10 to 15 minutes in entropy that I would like to settle here. So if you see in entropy, for an internally reversible process, for an internally reversible process, we have ds is equal to of reversible is equal to integral del q by t of, integral is not present because we are writing del ds. So this is del q by t reversible, correct? So which means we can write del q is equal to t into ds. Just a bit of mathematics I'm doing here again. So if you want the total heat that is getting transferred, so heat interaction is equal to integral over TdS, which means if you want to calculate heat interaction geometrically, you have seen that if work interaction is equal to integral PdV, work interaction is equal to integral PdV. So now if you see the case, if you have PV axis, P and V axis, now see here, when you have P and V axis, what happens? Suppose if there is some random curve which is pressure as a function of volume, and if you want to calculate the work interaction in this process, what could you do? If W is equal to integral PdV, then what you have done here, you would have find out what is this area, and this area is equal to the work interaction in the cycle, in the process, correct? Work interaction in the process. Similarly, now if I plot TS diagram, TS specific entropy axis, and now suppose if I have some random process, of course let us suppose entropy is increasing, so T is some function of entropy, then what do I need to do to get heat interaction in this process? If this is work interaction, which is the shaded area which is here, for getting heat interaction, what could I do? If there is integration, which area I would like to find? If the process is between these two states, this is this area, correct? And this area is heat interaction. It's simple mathematics, integral y dx will gives you the area between, if you are having limits from a to b, but of course process initial and final states are fixed, so you know the initial and final states. So if you know the process and if you know the initial and final states, you can calculate work interaction as well as heat interaction. So if you see, this is heat interaction in the process. Okay, so now one important thing is, if a closed system is undergoing a cycle, thermodynamic cycle, for by first law of thermodynamics, del Q minus del W is equal to du, correct? So by first law of thermodynamics, if the system is undergoing a cycle, then the initial state and final state of the system is same, because if the system is undergoing a cycle, and if the initial and final states are same, what could be the change in internal energy? Internal energy is U final minus U initial, and it's a point function, and it doesn't depend upon the path in which the cycle is taking place. So if you talk that, what's the total change in internal energy by a closed system executing a cycle? It is 0, correct? So del Q is equal to del W. So which means if you see for cycles or for a process, this is what you have. So if you apply this for a cycle, see, by first law of thermodynamics, for a closed system, executing a process, for a closed system executing a process, we know del Q is equal to del W. So for a cycle, if you see this, for a cycle, actually this is plus del W, del U, I mean, sorry, this is, let this, remove this here, plus du. So if this is the case, for a cycle, we know del Q is equal to del W. So if you integrate this over the same cycle, which implies area of, you can say area bounded by TS diagram on area bounded by cycle on TS diagram is same as area bounded by cycle on PV diagram. Correct? Because cyclic integral of this term will give you the total work interaction that's taking place in that cycle, and cyclic integral del Q will give you the total heat interaction that's taking place in this cycle. So which means if you plot a cycle on PV and TS axis, the area bounded by both the curves is same if the system is closed and if it's executing a cyclic process. Clear? Did you all understand why these two areas should be equal? Because if del Q is equal to del W, means whatever the functionality this has, if the same functionality is available here, then if you integrate between the same limits, means basically from the initial point to the final point of the cycle, so then these two quantities should be same. And you have seen just now, if this is the process, then if it have cycles, this integration has to be replaced with a cycle on the integral. So if you draw these two diagrams, you know, these two areas will be equal, which means if you draw a cycle on a PV diagram or on a TS diagram, the directions and the magnitudes of area bounded by both the cycles should be same. Clear? Understandable to all of you? Did you all understand why area bounded by cycle on TS diagram is equal to area bounded by cycle on PV diagram? Because total change in internal energy is 0. Clear to all of you? Yes, Vamsi, Arvind, Vijay. Okay, Chanav, fine. So see here. So normally if you draw any cycles, there will be some get questions, you know, they will be asking you PV, suppose if there is some cycle, something like this, which is a power producing cycle, then you know the TS curve also looks similar to this, you know, something like this, such that this area 1 and if this is area 2, then the relation between both the areas is area 1 is equal to area 2. So sometimes they'll give you different polygons for which you can find area. For cycle, of course, it's pi r square. They'll give you sometimes a rectangle, triangle, and all these things. The ultimate aim is to make you to find, you know, the coordinates. Like basically, if I give you a rectangle here and if I miss some coordinate, you can calculate by using this relation. Area 1 is equal to area 2. Okay, so now before going for exergy, I want you to discuss, I want one more topic to discuss with you. So entropy balance equation for open systems. Entropy balance, because I don't know, I'm not sure whether I'll teach you applied thermodynamics or not, but if someone teaches you, you'll be acquiring this term, these things of entropy. So I'm teaching you this. Entropy balance equations of open systems means basically where mass interaction is also allowed. Okay, so if you take this as a case, so see here, if you have a control volume, something like this, this is not a straight line. Okay, so let us suppose things are like this. So now definitely if the system is open, some mass tries to comes in at a rate of m dot I, and also some mass tries to go out, m dot out, and this is mass of control volume, and let S CV is the specific entropy of the control volume. So now if you see this, and let us suppose there is some energy interactions that are taking place with respect to this control volume. So there can be some heat interactions, some work interactions as well, all the things in general. So now if you write the If possible, please say the importance of mean temperature of heat addition in a Rankine cycle. I will tell you. So see here, if you see clearly entropy balance equations of open systems. So if you see m dot, see basically let us write the conservative equation which I have already written. Entropy generation, that is, I mean rate of entropy that is going in minus a rate of entropy that is going out plus a rate of entropy that is getting generated within the system should be equal to rate of this total entropy change of this control volume. Correct? This is the basic entropy balance equation that we have. Means whatever the entropy that is entering is equal to something that is coming out plus something that is getting stored. And also along with this entropy addition, because of the irreversibilities we have seen, there will be always some entropy generation within the system. Correct? If the process is irreversible. Of course, if it's reversible, then this S generation term will go to 0. But let us consider the case this is not reversible. So what happens? There will be some part of entropy generation. So now if you apply this for adiabatic turbine, turbine, of course turbines are generally insulated because you don't want the heat to escape out of the turbine, because whatever the heat you are supplying, you need to convert that heat to work in turbine. So from turbines you don't want to lose your heat intentionally, so you'll insulate the turbine. So for adiabatic turbines, executing a reversible process, because as people are talking in applied thermodynamics, we'll be dealing with a lot of cycles like a Rankine cycle and gas power cycles and all these things, where people will be representing isentropic terms like isentropic efficiencies and all. So I would like to discuss these things now. So for adiabatic turbines, executing a reversible process. So see carefully. For adiabatic turbines, executing a reversible process. See, let us suppose we have a turbine something like this. Of course, let us assume this is giving out a work W by taking some input heat and some output it's leaving, of course. So now this turbine is perfectly insulated. Okay. Anyhow, you will be trying to do the perfect insulations to the turbines by providing a very good insulation to the turbine casing outside. Normally, if you see the physical construction of the turbine. Okay. So now, since this is for any control volume, so now if you apply this here, look, entropy that is getting in minus entropy that is getting out plus entropy generation rate should be equal to rate of change of entropy of the control volume. But we know generally these devices operate at steady state, because I told you why they should operate at steady state in the applications of first law of thermodynamics. Did you remember why they need to operate at steady state? Did you remember? Okay, whoever is not present in that class, I'm repeating it again. See, if devices are running in steady state for control volume, the rate of change of mass within the control volume is 0, and also a rate of change of energy is also 0. Or you can write simply, for the time being, let us not consider rates. Let us consider this energy of the control volume and mass of the control volume. During steady state of operation, these two quantities has to be 0, because see, and generally that's how in steady state actual turbines and compressors operate in engineering applications. Because see, let us suppose some 10 kg mass is going in. Okay, 10 kg per second steam of 10 per kg per second of mass flow rate of steam is going in, and let us suppose only 5 kg per second is coming out, which is non-steady. Then what happens? For every second, 5 kg of steam gets stored inside. Correct? And your turbine has a finite volume, and after some 100 to 150 cycles, your turbine gets blocked, because your complete turbine is filled with some mass. So generally, you want to operate these devices in steady state, so that there won't be any mass accumulations inside. Similarly, there won't be any mass depletions inside, so that this device will have a mass fixed at all the times. Similarly, energy. Now let us suppose 100 joules of energy is going in, but only 50 joules is coming out. Okay, by some source. Then what happens? For every cycle, 50 joules of energy gets stored inside. And if energy is getting stored, internal energy of the fluid increases, which means temperature increases. But these turbines and all, they have temperature limits for the materials. Okay, so you can't allow either energy to store inside, or you also can't allow either mass to store inside completely. So then you need to operate these devices at steady state, which means the mass of the control volume has to be fixed. Means whatever is coming in, that should go out. Means these two mass flow rates, m dot I and m dot out, are to be same. And also energy of control volume has to be change of energy of this control volume has to be 0, which means whatever the energy that is coming in, that should go out. So if this is the case, if we assume steady state, if we assume steady state, then what happens to this term? Rate of change of entropy of the control volume. Please tell me what happens to this term if we are assuming steady state operations. At steady state, properties are constant. So if you see, if properties are constant throughout, of course homogeneous we assume. So if properties are constant, what could be the rate of change of this entropy of the control volume under steady state? It is 0. Entropy is not 0. Okay, but rate of change of entropy is 0. Entropy change rate is 0 at steady state. If this is steady state, now see, entropy can come in to the system through two means. One is through mass, it can come inside, or through heat transfer, it can come inside. So we can write this entropy inside as entropy in due to mass plus entropy in due to heat minus entropy out due to mass plus entropy out due to heat, and this has to be 0 because in a reversible process this entropy generation is 0. We have seen, correct? So if this is 0, and of course turbine is well insulated, which means the entropy which is coming in or going out, they should go only to masses but not heat, because turbine is completely insulated, so there is no heat interaction that can take place within the system. So if you consider this, entropy inlet to the system because of heat and entropy outlet to the system, I mean from the system because of heat, has to be 0, which means you can see one thing clearly. Entropy inlet due to mass is equal to entropy outlet due to mass. So this implies in mass flow rate into S in is equal to m dot out into S out. But what do we know? If system is operating under steady state, both in mass flow rate and out mass flow rate both are same. So you can cancel them, which means S at inlet is equal to S at outlet, which means the process is isentropic. Process is isentropic, and this is the case for adiabatic turbine. Adiabatic turbine, adiabatic turbine basically producing, undergoing a reversible process. Undergoing a reversible process. Okay, so if you want, you can see this expansion inside the turbine is isentropic. So now, but in practice what happens? Irreversibility is everywhere. So if you see in actual practice, what happens? In actual practice, under steady state, see what happens. S dot in due to mass plus S dot in due to heat minus S dot out due to mass plus S dot out due to heat plus S dot generation is equal to 0, because in steady state anyhow change in properties is 0. But if you see, since the turbine is well insulated in practical situations also, even though there will be very minute heat loss from the turbine, we neglect that when compared to the enthalpies which are at very high values. So if you see, this entropy inlet due to heat and entropy inlet due to out both are 0, because the turbine is very well insulated in actual practices also, because if you don't put a good insulation, what happens? Heat inside the turbine tries to escape out. So to avoid that, we'll put this. So this implies S dot in due to mass plus S dot generation due to mass is equal to S dot out due to mass, which means if you see, the outlet entropy is a bit more than this inlet entropy because of this S dot generation in order to maintain the turbine at steady state operation, correct? So if you see, now if I try to draw these two conditions, means basically if you see, I think S outlet will be a bit greater than S. Okay, let us remove these dots. So see here, S inlet plus S generation by m dot inlet or inlet or outlet, because at steady state both are same, doesn't matter. So let us write m dot mass flow rate of course, if you divide with this, is equal to S out. So here outlet entropy is a bit more than inlet entropy, but in reversible case, whatever entropy is coming in, I mean, what's the property of the entropy at the inlet condition, same is the entropy of the outlet condition. But here if you see this outlet, sorry for this, the outlet entropy is a bit higher than this inlet entropy because of this term. And you know, this S dot generation is always positive. Again, this chart is not working, just a second guys. Let me see in my mobile, otherwise I don't know what you're talking. Okay, so see here, so if you see this S out means entropy at the exit condition of the turbine is equal to something that is at inlet plus some positive quantity, because M dot is always positive and S dot generation is also positive, which means if you try to draw this diagrams on a HS plot, enthalpy versus entropy plots, see here what happens. Let us suppose I am plotting enthalpy and here it is entropy, and let us suppose two constant pressure lines or something like this. This is looking like a pure straight line. So this is some P2 is equal to constant at some higher pressure, and this is at P1 is equal to constant. So now see, if you take initial reversible case, if this is state 1 at higher pressure, now that steam should or whatever the working fluid that is here should expand to the state 2 isentropically, correct? Because you can see here clearly, because at inlet condition, I mean when the process is taking in a reversible place, this entropy at inlet is same as entropy at outlet, which means if these two entropies are same, then definitely the process should be isentropic and it should be a vertical line. But in actual practice, what's happening? S at outlet is slightly greater than S at inlet. Means if this is S at inlet of the turbine, then your entropy is slightly changing, slightly increasing, correct? This is S outlet. So if you see now, let me draw this clearly so you can see things. Okay, so now if you see, there is small difference between these two values, correct? This is 2 actual case, and this is of course isentropic case. So now if you see, H2 actual is greater than H1, I mean H2 isentropic, correct? Did you all understand till this point? When entropy is increasing, but when pressure of the devices are fixed, then this process 1 to 2 actual will run something like this with the entropy value slightly increasing, correct? Did you all understand why I have done this actual line a bit to the right of this line? I want you to respond. I'll enlarge this diagram, or else if you would like to see this in a broad scale, so see here. H, S, and let us suppose there are two constant pressure lines, P2 is equal to C and P1 is equal to C, which are basically the inlet at the the inlet condition of the turbine, and P1 is equal to the exit pressure of the turbine. Basically in a Rankine cycle, if you see, this P2 is the boiler pressure and this P1 is the condenser pressure. We'll see, I mean, whoever teaches you applied thermodynamics, they'll definitely teach you this. So if you see this, from my intention as of now, P2 is greater than P1, that's it. Okay, so from 1 to 2, the isentropic process will look something like this, a vertical line, correct? So 1 to 2, this is isentropic process, isentropic. Next, actual process, if you look for, will go something like this, to actual, because if you see the entropy outlet S out here and S out in actual case, S out in actual case has to be more when compared to the isentropic case, because of this term, S dot generation by M dot term. S dot generation is always positive, so definitely this S dot out in actual case will be more when compared to the isentropic case. So now if you see, this value is H1, this value is H2S, and this value is H2 actual. So now if you see, H1 minus H2S is the actual work that you can get out of the turbine, because if you apply steady flow energy equation, work done is nothing but delta H. So if you see, of course, minus delta H, because H2 minus H1 and enthalpy decreases in a turbine, this. So this is the maximum possible work that the turbine is capable of doing under these conditions. But because of this irreversibilities that are getting in, what's the actual work that you are getting? What's the actual work that you are getting? H1 minus H2 actual. And when H2 actual is more than this H2 at isentropic conditions, this difference H1 minus H2A is actually less than this difference H1 minus H2S. And this difference is nothing but the work done in a turbine. So if you see here, H1 minus H2S is greater than H1 minus H2 actual, and which of course tells us work done in an isentropic case is more than work done by the turbine in actual cases. Correct? So if you see, we'll define one term here which is called isentropic efficiency of turbine. Isentropic efficiency of turbine eta T, yes, or you can write isentropic, whatever you would like to write, subscripts. Isentropic should be equal to, means when the turbine is capable of producing H1 minus H2S difference as work, out of which it's producing only H1 minus H2 actual. And this term means, this is the maximum amount of work the turbine can produce under these given conditions, but this is the actual work the turbine is giving. So this ratio of these two is called isentropic efficiencies of the turbine, and you can see this on a HS plot in this way. So when you are dealing things in applied thermodynamics, people may ask you to calculate one of this. They'll give you isentropic efficiency of the turbine, and out of these 4 values, they'll give you 3 values. So you can find the 4th value. It's a simple thing. Okay, clear to all of you why isentropic efficiency definition is this? If you are okay, we'll go for compressor case. Clear to all of you? Okay, this chart is not working. I'll check here. Yeah, when we apply for compressor, we will get S out greater than S in. Yes, of course, I'll show you for compressor which is high. So please respond. Did you all understand this? Vamsi, Yugandhar, Chinawa, clear to all of you? Okay, Vamsi? Okay, so see here. Now we'll go for compressor, isentropic efficiency of a compressor, which is also an important thing when you deal Brayton cycle, gas power cycles basically. So see here. Isentropic efficiency of a compressor. So see here, what's the case when you have a compressor? So normally if you write compressors would look something like this. Geometrically construction. So if you see compressors where you will be inputting some work, because of which a fluid which is at some low energy will be transferred to a point which is at higher energy. Correct? This is the construction of a turbine. So we'll be putting in some fluid which is at some energy level, and you'll be adding some work, because of which the energy of the fluid will get increased. And generally compressors, they increase the pressure energy of the fluid. So if you see, okay, so now if you see again for actual case, since same as for turbine, because you'll also insulate compressors in practical conditions, because whatever the work that you are putting in, you don't want that work to go out as heat. Okay, because if heat is going out, again this energy, the time taken to reach this energy will be more. So compressors are also practically insulated. So if you see this, for actual case, S out will be equal to S in plus S dot generation divided by M dot. Okay, since I am assuming steady state and all this process, so I am putting M dot, I am not putting M dot in or M dot out. So for isentropic case, Or else you can write for reversible case, S out will be equal to S in, which we have seen in case of turbine as well. Equations doesn't change, but of course work is the only the direction of work interaction is only changing. Turbines will generally give you work output, but whereas compressors, they consume your work input. So if you try to plot this process of compression, for example, if this is P1 is equal to constant at the lower pressure at this junction, and at this junction let us suppose P2 is equal to constant, and the pressure stage of this compressor is to raise the pressure of the fluid from P1 to P2. So now if you try to draw the HS diagram, see here. Yes, H0. So see now, let us suppose you have two constant pressure lines. P1 is equal to constant. Okay, let us go a bit this way. Okay, so see here. So this is P2 is equal to constant, and for example, this is P1 is equal to constant. So let us suppose you are compressing the fluid. Now, if you are compressing the fluid in isentropic case, how would the fluid look like? If this is your state 1, and yeah, clear to all of you? Okay, because this chart is not working. So see here, if P1 is equal to constant, and if you are compressing the fluid in a reversible case, then S outlet should be equal to S inlet. Means the compression that you are adopting is isentropic compression. So which means the compression should be carried out something like this, 1 to 2. But in actual practice, what's happening? Your entropy out is greater than S in because of this positive term. So if you see in actual practice, what happens? Did this line get tilted towards right? So please see, when S out is equal to S in, let me draw the lines tightly so you won't have any misunderstandings in the concepts. Okay, so 1 to 2. Okay, but in actual case, your entropy has to increase. So let us suppose the process is something like this. This is 2 at isentropic case, this is 2 at actual case, because your entropy has to increase when compared to the inlet conditions. So now if you see, this is not a straight line, there will be some curvature for that. So we'll see this. Okay, so now if you see, this is H1 and this is H2S at isentropic conditions, but this is H2 actual. Correct? This is what you have. So now if you want to talk about isentropic efficiency of compressor, then this is equal to C. You want to raise the energy of the fluid from H1 to H2. Correct? And work input required is equal to, since I am writing input, it's nothing but H2 minus H1. When you are, in compressor, if you are changing the state of a fluid from state 1 to state 2, then obviously this H2 minus H1 is the work input that you are providing for this compressor in order to raise this pressure from P1 to P2. But now see what happens. In isentropic case, H2S minus H1 is the work that you could have supplied, is the W input to the compressor. W input to the compressor. But in actual cases, what does it happen? In actual cases, you will be having H2 actual minus H1 is the work input to the compressor. Work input to the compressor, which means whenever there is some irreversibility and there is some entropy generation, definitely these 2 points, these two doesn't get matched with each other, correct? Because obviously H2A will be more, which means you can see, since in the graph H2S minus H1 difference is this, you can say this as H2S minus H1 is this, but if you see, this is the difference between H2 actual minus H1. Correct? So now if you see, normally this much amount of energy is sufficient to raise the fluid from state 1 to state 2. but because of the irreversibilities, this is happening, which means out of every, for example, if let us suppose if the difference between these two is 20 kilojoules, something like 20 kilojoules, for example, means out of every 100 kilojoules of energy that you supply to the fluid, only 20 kilojoules is getting, I mean, only 80 kilojoules is getting supplied to the fluid in raising the energy of the fluid, correct? So see here, this much portion is wastage because of this irreversibility. So initially if you are supplying 100, then this much portion, which is the difference between these two, is getting, wasted because of this irreversibilities. So if you want to define the term isentropic efficiency for the turbine, I mean of the compressor, so see here carefully, is equal to, see, the minimum amount of work that is required for you is H2 isentropic minus H1, but the actual work it's consuming is H2A minus H1, and this difference is always, this ratio is always less than 1, and this is isentropic efficiency of the compressor. If you see the definition of efficiency, I told you clearly, desired output by required input, correct? This is the common definition I gave you. Means to get this desired output, what is the required input that you need to supply? Any comments? Because this is not working. So see here, correct? This is the common definition I gave you for efficiency, which is desired output and the required input to get this desired output. Now the desired output here is, in this case, is to raise the energy of the fluid from this level H1 to H2S. So the difference between these two is the desired output. Means we want this much of energy to add to the fluid which is working inside the compressor. But because of irreversibilities, what is the actual energy that you are putting in? What is the required input in order to raise the enthalpy of the fluid by this difference? This is the actual required input we are putting when the compressor is having some irreversibility that's taking place within this. Okay, so that's why the efficiency of the compressor is this. See, you need to always remember this formula, because you are planning to add this much of work to the compressor, but in order that the fluid gains this much amount of work, actually you need to supply this much amount of work, H2A minus H1, because some part of the supplied work is always getting we'll see why there is energy destruction. That's why the chapter exergy is coming, but this is what it's happening, correct? If you see the case of turbine, okay, so see here, this is the case. Basically, efficiencies of the turbine, and turbine generally don't capture any inputs, it captures only this input. So this is the formula for isentropic efficiency of the turbine, and similarly if you see for isentropic efficiency of the compressor, this is the formula. So did you all understand why these things are happening? This chart is not working again. Okay, so see here, fine, it's working. So did you all understand why isentropic efficiency of the turbine and compressors are this way? If you all understand, please say yes. If you don't understand, you can ask me something that troubles you, because you'll be seeing some expressions like isentropic efficiencies of turbines, compressors, all these cases when you go for some applied thermodynamics, where you shouldn't. This graph, Arvind, so see here, if you understand these two equations, when the case is reversible, S outlet should be equal to S inlet. Means if I want to draw a process on a TS plane, basically this is HS, of course, sorry, on a HS plane, if you see, if I want to draw a process such that my initial entropy and final entropy is same, but enthalpy is increasing, then the only thing I can draw is vertical straight line, correct? Next, if the entropy is increasing along with enthalpy, so then entropy should also increase along with enthalpy. Of course, this is a curvature, we'll see later, that's not the part of this basic thermodynamics course. We need some advanced analysis for identifying the nature of this curve. So see here, 2S and 2A. Now, this difference H2 actual minus H1 is the total energy that you are supplying to the compressor, but out of this H1 minus H2A total enthalpy difference that you are supplying to the compressor as work input, only this H2S minus H1 energy is supplied to the fluid, and remaining energy is getting wasted because of the irreversibilities. Okay, so clear to all of you? Did you all understand now? Okay, So this is what basically I would like to talk on entropy. This, I think this much is sufficient. But before summarizing, before going for the next chapter, I would like to summarize all the results that we obtained till now. Okay. So please respond for each and every result that I write on board. Okay, because that's really important for us. So for any process between states 1 to 2, delta S of the process 1 to 2 is equal to cyclic integral, normal integral del Q by T within the process 1 to 2 plus S generation within the process 1 to 2. And you know, we should remove this word any, because this entropy generation depends upon path. Correct? We have seen this. So let us summarize all the results that we learned in entropy. For a process between states 1 and 2, change in entropy of the process is given by entropy change due to heat transfer plus this for closed systems. Of course, we are dealing for closed systems, because in open systems you can have mass interactions as well. So now S generation is equal to 0 if process is reversible. If process is reversible, greater than 0 if process is irreversible. Correct? I told you why entropy generation, if it's present, why it's always positive. That's why, you know, the name is also given generation. You know, if there is some generation, that means there is some positive effect. Okay, so greater than 0 if process is, you know, irreversible. If you would like, you can name this as summary of this entropy, because, you know, results are very important here. Next, this is first thing. Second, entropy change of a process. Entropy change of a process. Now I will say it will be always positive. Will you agree with me? I will say entropy change in a process will be always positive. Will you agree with me? Say yes or no. No. Why? Yesterday you yourself told, many of you, that entropy of a process will always increase. No, correct? Because we have seen yesterday. Why? So entropy change of a process can be positive, negative, or 0. No. Good. All of you told no, it's correct, because we have seen in yesterday. Why? Because entropy change within a given process can either be positive or negative or 0. Means if a process is happening, it can increase, entropy can increase, entropy can decrease, or entropy can remain constant. But S generation is always positive if it's present in any irreversible process, correct? So entropy change of a process can be positive, either negative, or it can be 0. Third point, S generation is always positive. Okay, next, one important point I would like to add. Entropy is a point function. Entropy is a point function. But entropy generation is a path function. Correct. Path function. Okay, next, these are few results. We'll write some more results now. See here. Okay, anyhow, we'll go for the next page. So see here. Five. For the process to be isentropic, now tell me, for the process to be isentropic, should it be reversible adiabatic? Is it mandatory? For the process to be isentropic, is the process has to be reversible adiabatic? No, we have seen yesterday, correct? Because if there is some heat rejection from the system, and whatever the entropy that is getting generated within the system is going out, then you can say for the process to be isentropic, the process need not be isentropic. Sorry, need not be reversible adiabatic. But if it's reversible adiabatic, yes, it is isentropic. I agree. But for the process to be isentropic, definitely it need not be, reversible adiabatic. Because you can have an irreversible heat rejection process. An irreversible heat rejection process can be isentropic. Because in this equation, this is for any process. So if you see, if there is some heat rejection, then this term will be definitely negative, correct? Because heat is getting out of the system. So if numerically this S generation is equal to this integral del Q by T, means whatever the entropy change is there because of this integral del Q by T, if this is same as this entropy generation, then this delta S will be 0. Next, these are all good points in which generally you told some other answers when I asked you these questions for the first time, correct? But I'm happy now all of you are answering them correctly. Okay, so next we'll write one more question for open systems. Then entropy rate in minus entropy rate out plus entropy generation is equal to delta S dot of control volume. But of course, we are dealing only with these things, steady state things. So we can write S dot in due to mass plus S dot in due to heat minus S dot out due to mass plus S dot out due to heat plus S dot generation is always equal to delta S dot of the control volume, and you can apply this equation for any of the control volumes. Correct? Now for any control volume, yesterday also we have seen that wall case, when 100 kilowatts of heat is flowing to one side of the wall and another 100 kilowatts is flowing to other side, we have used this equation. Correct? For any open system, you can use this equation, and also you can deduce entropy change for a process in a closed system. I have already shown you in the lecture, in the 2 lectures ahead, how from this equation you can get the first equation that we wrote today. Like from this equation, we can deduce this equation. I have shown you how to deduce this. Correct? So next. For two bodies at T1 and T2 temperatures respectively, at T1 and T2 temperatures respectively, at T1 and T2 temperatures respectively, of course, if T1 is greater than T2, if the bodies attain thermal equilibrium, by virtue of reversible heat transfer. Oh, I didn't write 7th point. Okay, so this is 7 then. You can always, I have a poor maths teacher, you can help me out for that things. So if the bodies attain thermal equilibrium by virtue of reversible heat transfer, or you can write by reversible heat exchange, then the equilibrium temperature, TF is equal to, can someone tell me the expression for this? I have derived this expression in class. So please someone tell me what could be the answer for this. It's arithmetic mean or geometric mean of the temperatures. When the heat transfer is reversible. When the heat transfer is reversible. All of you are telling arithmetic mean. Is it? See. We have listed something like this before. Correct? So see here, two bodies of same thermal capacity are exchanging heat in a isolated reversible system. Then the final temperature of the bodies. This is the analysis we have done for reversible heat exchange. For irreversible heat exchange, this is the analysis we have done here. Correct? So if you remember, for reversible process, this is geometric mean. And temperature difference between, heat exchange between two finite temperatures means heat exchange between finite temperature difference is always irreversible. So if you see, this is the analysis we got when the process is irreversible. But when you are assuming reversible heat transfer, means the heat transfer is occurring very slowly, and practically if you see, that time attained by these two bodies to attain thermal equilibrium is very infinitely large. So in that case, we have seen total entropy change equal to 0, and after this analysis we have seen this is geometric mean of the temperatures. Correct? Then why are you telling arithmetic mean, all of you? We have done this. Correct? So we can write TF is equal to square root of T1 into T2, which is geometric mean of T1. Some mosquitoes are coming inside. T1 and T2. Okay. Clear? So this is what we have, and area of the cycle on TS diagram, basically temperature entropy diagram, is equal to area of the cycle on PV diagram. Please don't mind if I am killing some mosquitoes, because they are disturbing me. So we have cyclic integral TdS is equal to cyclic integral PdV. Okay. So this is what we have seen. Correct? Apart from this, is there any points that you answered wrong when I asked you for the first time? Clear to all of you? So these are some good, these things. See, I'm not discussing all the cases. Okay, see, if you observe, if you know this equation, you can calculate entropy change for any process that's happening. Okay, and you have seen in yesterday's class, basically we have detected all the problems from this basic equation. Did we do that? Is this the only equation we used to solve yesterday? Correct? So this is entropy. Okay. And I would like to tell you one thing, one important statement actually, which was, experimental as well. The entropy of a pure crystalline substance, the entropy of a pure crystalline substance at absolute zero temperature. Absolute zero temperature. 0 Kelvin is 0, because for gases and all, if you see mosquitoes, for gases and all, if you see what happens as per kinetic theory of gases, at absolute zero temperature, molecular motion stops. Correct? This is what we learned, because pressure is directly proportional to something called temperature. We have seen both pressure and temperature are being we have seen in the initial introduction to thermodynamics chapter. In the first chapter, pressure and temperature are both interrelated, and pressure of gas is nothing but the normal average of the collision forces exerted by the molecules on the walls of the container. Correct? So this is what we have seen. If there are some molecules which are colliding with the container at all points, then because of some random motion they have, then what do? We put a pressure gauge here, and we have measured the absolute pressure, the gauge pressures of this gas. Correct? And I told you, Pressure is due to the molecular momentum of the molecular momentum exchange of the gas particles. So if temperature is absolutely zero, then will there be any kinetic energy for these molecules? Please tell me, if temperature is absolutely zero, will there be any molecular motion for these molecules? Motion for these molecules? No, because as per kinetic theory of gases, we know kinetic energy is directly proportional to temperature. So if T is absolute zero, these molecules don't move, which means the system doesn't have disorderness, basically. Okay, so this system, which means all the molecules, what they do? They simply sit without moving. Something like this, correct? So what happens? There is no disorderness because molecule stops moving practically. But for crystalline substances, in gas molecules, at least you have something. Like example, in gas, molecules can move from one place to one place. But if you talk about pure crystalline substances, means basically in solids, are molecules capable of moving? Internally, they vibrate about their mean positions if temperature is more, correct? Normally, if you see this thing, crystalline substances, something like this. You see some diagram similar to this in your 11th class physics textbook. Means on the hardcover of your 11th class physics textbook, correct? There will be a solid which they will be connecting by springs like this. Correct? You remember? There will be one solid like this. Yes or no? Let me remove this part. It's not looking nice as far as diagram is concerned. So if you see front view of the solid looks something like this, correct? Why I have connected with springs? Because when the temperature of this body, see, this is a complete body and I'm looking in atomic level. So the temperature of this body, if you see, is greater than 0 Kelvin, then what these molecules do? Will they sit silently here? What they try to do? They'll start vibrating about their mean positions, correct? And that's what we have told as vibrational translation energy, correct? Vibrational energy we have discussed. If you see in the second law, in the second chapter, in concept of heat and work, in the first lecture, I was talking about energy possessed by systems, correct? There, I told you that this is the energy due to vibrations when temperature is more. Yeah, at every point they vibrate as long as the temperature is greater than 0 Kelvin. So if they are vibrating, then if temperature comes to 0 Kelvin, then will they start vibrating again? No, they will be sitting simply. Normally, when this molecule is vibrating from this mean position to this mean position, this has some disorderness. Means there is some probability for locating the position of this molecule because it starts vibrating. And complete solids, even though they don't have macroscopic motion, but microscopically all these molecules will tend to vibrate about their mean positions when temperature is beyond 0, and that's how actually your heat conduction goes on, correct? Because if you are conducting heat, if you are putting one end of the solid to a high temperature, what happens? Heat gets transferred to the body, and as a result, this molecular vibrations, see, for example, let us suppose one person is standing in front of you. Then if someone behind you pushes you, then what happens? You obviously push this person, correct? You can see this in a movie ticket line generally. Of course, nowadays we have book tickets and Just My Show and all these things. But olden days during my childhood, if you see, this thing used to happen. So similarly, when you are supplying some heat to this, these molecules are so close in solids, of course, pure crystalline substances. Then what happens? The molecules which are here will start vibrating, because of this bond energy, they'll start transferring heat to this molecule. Again, this molecule to this. So like this, this heat gets transferred from one portion to another portion. But now if the absolute temperature is 0, these molecules without doing anything, what they'll do? They'll sit silently here, which means there is no disorderness of the molecules, but they are fixed positions with some good order or crystalline geometry of the solid. So you can see this is at absolute temperature, this is 0, means no disorderness, because entropy is nothing but measure of disorderness of a system. So you can see clearly no disorderness, and this statement is called third law of thermodynamics. third law of thermodynamics. Clear to all of you? Understandable? So why at 0 Kelvin, absolutely 0 Kelvin, yeah, entropy is 0 at that case. So if you see at absolute 0 kelvins, these molecules don't start vibrating, they don't have any disorderness, but they'll sit quietly at their lattice points basically. Okay, so that's why at absolute 0 kelvin there's no disorderness for the system. Clear? I hope, I assume that you all understood entropy in a good way. Yes, if there is some difficulty you can talk to me, because I'm going to next chapter, exergy now. In entropy, if you have any doubt, you please ask me, or if you understand good, you please say here. Okay? Fine. So this summary points which we have written here are actually really important for us, because by looking at this equation we can identify entropy change of any system, and these statements you have answered wrong when I asked you for the first time in this course. Correct? Many of you told entropy change of a process can't be negative or 0, it will be always positive. But I have shown you the things. Yes, generation is always positive, of course. Entropy is a point function, but entropy generation is a path function. You need to be very clear between these two terms, entropy and entropy change. I have given you derivations for both the things. Correct? I have given a derivation for you in this course why entropy is a point function, and I also given you derivation for why entropy generation is a path function. Clear to all of you? So if this much is clear for you, then we solved problems in yesterday class. All the previous gate questions of entropy we solved in yesterday's class. So now we would like to go for another chapter, which is exergy. Then we'll see why in summer there are more power cuts when compared to winter. Okay, so we'll see that. And just give me a minute time. This board is a bit slow responding, so I hope you are understanding the things well. Correct? Did you all understand why this line is looking like that, that line is looking like this and all? So now please try to tell me one thing. If I ask you one thing here, last one point in this chapter, so please see. If I ask you, every process in the nature or every process occurs in a direction in which delta S of universe is greater than or equal to 0. If I say this, will you agree with me or no? Please tell me. If I say this, please tell me, will you agree with me or no? I'm awaiting your responses. So please tell me. Yes? Yes? See, don't answer by looking at my face expression. Okay, please answer with the knowledge that you have. Okay. Yes, generation? Correct. Because if you see universe itself is an isolated system. Correct? Because it can't exchange energy, because there is nothing outside universe to exchange energy. Similarly, it can't also exchange mass. So this universe, as we told, this universe is a isolated system. Isolated system. So if you want to talk about delta S of universe, you need to talk about delta S of universe due to mass transfer and delta S of universe due to heat transfer and delta S of, completed mass and heat, then due to S generation. Correct? Since universe is isolated system, you can't have mass interactions or energy interactions. So which means delta S of universe is always equal to S generation, which is greater than or equal to 0, which I have written here. Okay, so every process in this universe, yeah, I'm happy that many of you answered correctly. So every process in this universe takes place in the direction that delta S of universe is always greater than or equal to 0. Okay, so for example, if you see that day we were discussing one thing, there's a coffee cup on the initial day of this lecture. If you remember, there's a coffee cup in which there is some hot coffee, and let us suppose this coffee is at some 127. I think 127 degrees coffee is really difficult to drink, so let us make it 50 degrees centigrade. Okay, which is relatively hot, and the atmosphere is something around 27 degrees centigrade. Okay, so now let us suppose the coffee is giving heat to the outside this thing, and let us suppose the total heat is 100 kilojoules, something around this 100 kilojoules or something like that. Some heat is being transferred, or else let us go for some small value, 10 kilojoules. So now what it happens, if you see, delta S of universe is equal to delta S of system plus delta S of surroundings, and of course heat transfer between finite temperature differences is Sgen. Now if you see, this is equal to heat lost by this coffee. This temperature starts reducing, so finally it attains this atmosphere temperature if you keep that as it is on the table for a long time, correct? If you pour a hot coffee in a cup and if you put it like that in atmosphere, what happens? Because of the heat transfer between hot coffee and the atmosphere, practically this coffee attains the temperature of this ambience after some time. So since this coffee is an incompressible substance, because coffee is a liquid and coffee can't be compressed, for example. So if you see, if mass of the coffee that you are drinking is m and specific heat of the coffee is c, then ln Tf, I mean T ambient, you can write directly here. Okay. T ambient divided by T initial temperature, where initial temperature is 50 degrees centigrade. This much of entropy change is there for the coffee. Now for the surroundings, if you see, this amount of heat which is rejected by this coffee is gained by this atmosphere. So minus mc Ta minus Tf. This is the total heat that is given to the atmosphere, but of course this is at a temperature Ta plus S generation. Now if you talk about this value, this is heat addition to the atmosphere, because this atmosphere minus Tf will be this is Ta minus T initial actually, initial temperature of the coffee. So if you see, this value is always greater than or equal to 0, because logarithms generally they possess less values when compared to this Ta and all these things, correct? So yesterday we have seen integral del q by T plus q by Th, and you have seen since this Th is higher throughout this heat transfer process, this value will give you a positive value, and plus positive value minus something that is really small will give you totally which is greater than or equal to 0. And that's why generally heat goes out of the coffee, but it doesn't come into the coffee. Okay, because this delta S of universe is greater than or equal to 0. Okay, clear? So this second law is basically directional law. So it tells us in every day. See, in the beginning day of the discussion we learned that satisfying the first law of thermodynamics is not alone sufficient for a process to occur, correct? It should satisfy some other conditions. So that means for a process to occur, along with the satisfying first law, it also should satisfy second law of thermodynamics. Means along with energy balance, it should also show the direction. So that's why this second law is called directional law. Okay, so you can write probably, if you want, second law tells us the direction in which the process has to occur, because every process should occur in the direction where delta S of universe has to be greater than or equal to 0. So you can write second law is, this board is not responding, friends. So second law of thermodynamics is directional law, which means it tells us along with the energy balance the direction in which the process has to occur. So if I ask you a simple question, like for this coffee environment example, that heat transfer occurs in the direction from coffee to atmosphere, correct? But if I ask you some complex procedure like for turbines and compressors and all these things, then you'll calculate this value and you will say the process happens in the direction in which this delta S of universe is always greater than or equal to 0. Clear to all of you? So that's why the second law gives the direction of the process actually in which the process will proceed. Clear to all of you? If you understand that, okay, so few of you are asking to start new chapter from Monday. Okay, so I have enough time to deal with thermodynamics, so no issues. We'll start on Monday. So tomorrow there is no thermodynamics class for you. We have 2 maths classes from 7:45 to 9:45 and 10:30 to 12:30. Okay, and of course I'll change the thumbnail for today's class as linear algebra, and this class also I'll change the thumbnail as entropy, lecture number 6. Okay. So we'll start probability tomorrow in mathematics close. Okay, so whoever want to attend probability, you please attend, because probability is a very good subject, or very good discipline in engineering. Okay, so then that's from my side. We'll meet on Monday. Okay, tomorrow we have maths classes on 2 sessions. Clear to all of you? Clear? So can we make a move for today? I'll provide you the notes, no issues anyhow. Okay then, thank you all. Have a nice time.